Physics 2211, Lab 1 Report. Constant Velocity by Wyatt R PHYS. Introduction to the lab. This lab observes an object in constant velocity traveling a small distance in a short amount of time. For this lab, air resistance and friction were ignored in all calculations. The purpose of this lab is to compare a visual observation of a moving object to a simulation created with Web v Python to explore the reliability of Newton's second law, even between differing visualization methods. Some of the principles of physics that will be used in this lab are Newton's second law and the principle of momentum. Here are some major results of the lab. The trajectory of both the observed position and predicted position were very close together when plotted. This shows very little variation existed between the more linear position over time graph of the object plotted in Web v Python and the more varied position over time graph of the object recorded and observed in person. This also means that the physics principles used are also reliable across mediums. Observing the object in motion. The system my group observed was a cart-like box on wheels. It slid across our surroundings, a low-friction table, with a meter stick behind it to measure the distance. The cart moved in the negative x direction, so the velocity in the tracker and VPython programs reflects this. Using tracker to determine velocity. To analyze the cart's motion, the group used a program called Tracker. Over a span of 25 frames, at 30 frames per second, the position of a blue square of tape was recorded on each frame. This allowed for us to monitor the change in the x-coordinate of the cart over time. Using the software, the following graph was generated using the x-coordinate data collected on each frame of the video, which shows the x-coordinate position of mass A, our cart, over the time in seconds. Seeing as the slope of this graph is fairly constant, our cart was in a state of near constant velocity. Net force of the object. As the velocity of our cart was deemed to be constant for the whole length of 25 frames, there was no form of acceleration present during our observation. In other words, there was no net force acting on the object while it was in motion. According to Newton's second law, the magnitude of the net force acting on an object is equal to the mass of that object times the acceleration of that object. If the acceleration of our cart was 0 over the span of 25 frames, that would mean there were no net forces acting on the cart, regardless of the cart's mass. Calculating velocity from position and time. To calculate the average velocity, normally one would take the initial velocity and add the final velocity to it while dividing the whole thing by 2. However, since our cart was under constant velocity, we're able to say that the final velocity is equal to the average velocity. To calculate the final velocity of our cart, the final position and time were recorded from tracker. Since the initial position and time both had a magnitude of 0, the change in both components were equal to the final values. Dividing the final position, negative 0.742 meters, by the time it took to get there, 0.8334 seconds, the average velocity was calculated to be negative 0.8905 meters per second. Plotting the motion in Web v Python. To visualize the object under an actual constant velocity, Web v Python was used to create a computational model for this purpose. The initial position, velocity, and time were defined, and the change in time for each step was also defined. A loop was created with the net force defined as the zero vector, since it was previously determined that there were no net forces acting on the cart. Finally, the object's position and velocity were to be updated over time. So, the position and velocity update formulas were applied in Web v Python. The velocity update formula relies on a change in velocity, which is caused by the net force acting upon the object. However, in this case, no net force acts upon the object, meaning the velocity will remain constant for the duration of the program's runtime. The positional update formula uses the velocity with units of distance per unit of frame to add to the position at a given time, in this case, every 1/30th of a second. Running the Web v Python code. After completing the code and inputting the variables such as the initial position, velocity, and net force, the program was set to output a visual and a corresponding set of data and graphs. The blue ball in the video here shows the object moving to the left from the origin, marked by the yellow ball. An exposition over time graph was also outputted as a result of the code, looking very similar to the one outputted by the tracker program. The only difference in the graphs is that the WebVPython simulation had genuine constant velocity, while the cart that was moved in person obviously had some change in velocity, as we only assumed constant velocity, not that it was truly constant. Discussing results again. With the outputted positions at corresponding times from both the tracker observation and WebVPython simulation, a graph was plotted in Excel comparing the two. Even though the observed cart really didn't have constant velocity, it got very close to being constant, only deviating from the perfect solution a tiny bit. These experiments prove the reliability of Newton's observations in the forces affecting the position of the objects, as when reconstructing a simulation of an object with his formulas, the results hardly deviate. What about error? As humans have made discoveries throughout history, countless errors have been made. Our small group of physics students is no different. One possible source of error could have been the position of the camera recording the object. With the end and start of the video being at the ends of the camera, the perspective is not fully flat, meaning the ends could appear stretched and throw off the observed position of the object. Also, the square tape we used came out very blurry in the footage, so the position of the cart may have been slightly wrong at some points. What if and what does it mean questions? What if the axes have been changed from negative x to positive x, their results would not differ, only reverse direction. The y-axes were not analyzed in this lab, therefore switching negative x and positive x will only have changed the direction of the velocity, not the magnitude. Our results would not have changed. What does it mean question? For the net force to have zero magnitude in the x direction, friction and air resistance would have not exist, which is simply not reasonable. In addition to these forces, other forces such as the push of the wind, slant in the surface, and particle interactions may all have had an effect on the observed cart. Therefore, it is also unreasonable to accurately say how many forces are interacting with each other in order to produce a net force of zero. My name is Wyatt R PHYS, and this was Physics 2211, Lab 1.